So, as introduced, I'm Martin Slepicka, a research assistant at the chair of computational modeling and simulation at the Technical University of Munich. And I want to present to you my topic, the fabrication information modeling, closing the gap between building information modeling and digital fabrication. Well, building information modeling as a holistic digital design methodology, I will not describe in detail today. I will just jump into the description of what is actually digital fabrication. And for this, I have some practical applications for the start. As you can see here, there are several houses that are already printed with additive manufacturing technologies. So digital fabrication is actually nothing new and also already kind of is established in the construction industry. In the middle, for example, there is the APIS core print, this round-shaped building you might already know. Then on the right side, we have the Winsun print of a multi-story building. And on the left side, there's the house that was printed this summer in Germany by a company called Peri. And they used a specific printing method, which is shown here. As you can see, you can directly input some installations like the sockets, and there's some voids in the wall. So they use a contour printing method, and you can fill them with insulating material or something. That was quite quick. I'm sorry for that. Yeah. Maybe it also represents that the printing technology used is actually quite fast, and they printed the whole vertical structure in less than 100 hours, which calculates to about 12 working days, which is quite fast for a project like this. Okay. In construction, there's several methods, AM methods already established and that can be used directly for printing concrete or even printing metal. And they can be classified into these two major types of methods. The extrusion-based methods, for example, they work on a principle that there is a printing nozzle which extrudes the material in the place you want to have material. On the right side, we have the powder bed methods, which works on the principle that there is a powder bed applied to a surface, like layer-wise, and this powder bed gets activated or bound at certain locations, as you can see here in the structures. And with that methodology, method, you get very refined geometries, but have the disadvantage that it is limited to a certain space. So because the time is short and the extrusion-based methods are a bit more interesting for this presentation, I will focus more on these methods. And they also have they're more interesting because they can be adapted in various ways. One way is, for example, the machine system that is used for the printing method. In the case of the Peri house, for example, a gantry robot was used, but you can also replace that and attach some extruder, something like this, to maybe a mobile concrete pump, which is has been studied by the Technical University of Dresden, and or even industrial robots, which is studied by by projects that I'm also working together with. Industrial robots have a lot more advantages. They can be used to print a lot more complex structures like these overhanging structures, or they can actually be used to print on existing material like the reinforcement here. And this is actually a different type of printing. This is called shotcrete printing, which also applies material through a nozzle in an extrusion-based way. Yeah. All in all, there are a lot of established AM methods which can or may be used in cooperation combined for a construction project. And I think it cannot be seen what is written there, but it's not important. The important thing is that each of these white boxes on the outside represents a company that created a machine system for specific AM methods. And each of these machine systems comes with their own software system, and the data that is necessary for each of these systems may look different. So the question is, can everything work together? Can we use multiple systems for one construction process easily? That is quite hard, like this right now. If you have to use multiple software solutions and have to translate in between them. So we identified a research gap here. Well, it is not quite new because it was already defined by researchers Duro and Oxman from MIT as fabrication information modeling, and that by their definition, this term was defined as a methodology designed to bridge the gap between virtual design tools and advanced digital fabrication tools. It is basically a methodology that chains all processes that are involved in a construction project from the design to the production, to the fabrication and use of the product together, and provide a seamless transition from each of these individual processes. Well, in construction, we don't use these descriptions. It's something I derived from other industries. This is actually something that is looked at in Industry 4.0 research, and it also applies here. Another thing was the step and see approach that was already implemented for subtractive manufacturing methods. This is actually an approach to describe machine control in the same data structure that the geometry and the semantic information is stored in. And something similar we are proposing with the fabrication information modeling for construction. So let us look under the hood of the term fabrication information modeling. What is it exactly in the term I want to present to you right here? Well, BIM, as I described earlier, is a holistic system that already takes care of design and some engineering tasks and also logistical tasks. And you can model a lot of information with that methodology. But what is not yet possible is to design fabrication information. Fabrication is still done separately from BIM, and could be integrated when using digital fabrication methods, such as additive manufacturing methods. And for this, we want to implement an intermediate layer, the fabrication information modeling methodology. And there's a question, what kind of information do we need, and how can we derive it from already existing BIM models, or can it directly be created for FIM and brought back to a BIM model. So yeah, what about the information? Is the geometry refined enough for fabrication? And what kind of information in the BIM model is actually necessary? And can we actually, do we need to define the material properties more accurately for the fabrication? And is some information missing? So, well, additive manufacturing methods allow for a lot more complex structures, and also allow for the creation of inner voids in structures, like shown a little bit here in this picture in the middle. So therefore, we need a lot more refined geometry data, and as best, it would be best to define the geometry by actually the motion of the robot system that is later used to create the part. In our case, we want to describe the geometry by the print path and the layer. And we want to define all the necessary parameters that are required for the fabrication. We want to define them in a way that they are linked to that path information. From that description, from the path description, we can then also derive a volume model that is more or less the as planned 3D representation of the part that is to be printed. Well, in the process, it looks more like this. We have maybe already existing BIM data. And then we can use translation processes, algorithms that use BIM information and create fabrication information. Yeah, for this, we actually need to look into what kind of object we want to print, what problem do we have? Like, do we want to print a wall or a column or something like this? So this translation is problem specific, and also, yeah, specific to what inner structures do we have and stuff like that. But it is still unspecific to what kind of machine system we use. So the film data still is decoupled from the machine control. In the second step, when we have the print data, we can use another translation algorithm to translate directly to machine control. Well, I did say it's unspecific to machine control, but it is still specific to the type of additive manufacturing that is used. So there's different kind of film information for extrusion-based systems and for powder bed systems. But in general, the translation mechanism is quite similar, and the information is about the same. Yeah, and with this, the information of the film, we can actually do simulations before we actually print the object, such as thermal conductivity simulations, to check if the object we planned actually works the way we want it to. And we can also do 2D simulations, like we take the print path and see if it's actually printable or not, if the robot control can be directly translated or not. Yeah, when does fabrication information modeling takes place? That is a big question, and we also want to be a bit open about this question. We need a certain amount of information to create fabrication information. We need some certain detail in the geometry and information about which type of AM method we are using, stuff like that. And yeah, but it is not necessary that we know what kind of fixtures we use on our raw print. So it has to come somewhere in here. But we will also want to be open to support the designer in decisions in early design phases. So we it's not directly linked to my project, but a project I'm working with and will have a lot of communication with will work on this design decision support system, where there will be a rule-based decision support for the designer to design BIM objects in a way that they can be fabricated with digital manufacturing methods. Yeah. So a little bit about the data structure itself. I mean, as I said, there's a lot of processes involved. So something like this. We have the BIM modeling itself, and there's path planning, and yeah, all the parameter tuning, and a lot of stuff that comes later. And if everything uses, every process is done in its own software solution and with its own data structure, communication between the processes is a little bit messy, as you can see here. It's not working like this. So what we want to build up on is working with open interoperability standards, such as the IFC standard, which is well established for the BIM methodology. Yeah, so what we use is the BIM information directly from this open interoperability standard, such as an IFC file, but it can also be represented as a database that is online and accessible. It doesn't really matter. It is based on BIM information. We worked with IFC entities and relations, but we want to make it as similar as possible to directly use that knowledge that has already been created. So what we create around this is more information on the fabrication information. So at first we have the core information, that is the print path, the layer information, process parameters and everything. And we create that by processes, path planning and parameter tuning, stuff like that. And that is not strictly given. So we can plug in any kind of path planning here. In the end, we just want to store the print path in the data structure to represent the movement. How it is created is not directly important for us. So we want to be open for different kinds of translation methods. So we use BIM geometry, use a certain kind of translation algorithm to create a path and store it in our data structure.
Martin,
we store it as a composite curve, which we linear reference some data directly to. Is there a question?
Yes, just to say you have 1 minute in your time. So if you need to wrap up, then you'll have to get on.
I'm a little bit delayed.
You can take 2-3 minutes if you wish. That's okay. Just to let you know.
That's fine. We also create layer information. This is directly used for the path planning. Any slicing tools uses layers to slice an object into 2D slices, and we can directly use that information to store a normal vector, which can be used to control the orientation of the robot if you use, for example, an industrial robot. And we can directly place the print path on that surface and reference it to the UV space of the surface. And yeah, this has also the advantage that we can directly do the printability check with it, and later on use it as a template for sensor data. From that, we can create 3D volume information, for example, a voxel model, and store the material distribution also into the data structure, which can be used for the thermal simulations, for example. Afterwards, we can use digital scan methods to store digital twin data. Like I said, it can be stored in the layers we already have from the path planning. And we can use this information for post-processing information. So how does it look if we want to transfer it to the motion, the robot control? We use the composite curve, which is put together from points, arcs, lines. Also, splines would be possible, which has very limited data. So we have a implicit description of the path, which can be directly translated into movement by either discretizing it to points if we want to have point-to-point movement, or use the elements for robot control interpolation methods like linear interpolation, circular interpolation, and can be directly converted into various kinds of programming languages for robots. We have tested that for clay extrusion, which was quite successful, and we also did some printability checks with Rhino and Grasshopper, which is also looking quite nice. And what we want to continue on later is working on the digital twinning and using scanning tools to store sensor data in the layer of the path planning process. Well, that's it. So in the end, we want to have a system that comes in between BIM and 3D printing. And as a final note, I want to say that this project is funded by the DFG and is part of a larger project that is called the TRR277, Additive Manufacturing and Construction. Thank you for your attention.
Great, thank you very much, Martin. I really enjoyed the presentation and the paper. Actually, I think you guys are addressing a very interesting problem. I'm waiting for questions coming from the audience.